Right now, as you lie here, photons that left the sun 8 minutes ago are still arriving at the place where you are, even though your eyes are closed and the room around you has gone dark. The sun does not know it is nighttime where you are. It simply keeps burning, the way it has burned for about 4.5 billion years, converting hydrogen into helium in its core at a rate so vast that 4 million tons of mass disappear into pure energy every single second. You cannot feel this, you cannot hear it, and yet it is happening, steadily, indifferently, while you rest. This is a strange thing to sit with, if you let yourself sit with it slowly. We tend to think of the universe as a fixed backdrop, a stage that stays the same while the small dramas of our lives play out in front of it. The stars we saw as children are the stars we point out to our own children. The moon rises and sets the way it always has. Nothing about the sky seems to be in a hurry. But the truth, and this is not a frightening truth, just a quiet and factual one, is that everything you can see above you is in motion, in transformation, in a process that has a beginning and, as far as scientists can tell, will eventually have an end. That word, end, tends to arrive with some baggage. It calls to mind a curtain falling, a scene cutting to black, something dramatic and final and maybe a little bit alarming. But when astrophysicists and cosmologists talk about the end of the universe, they mean something much slower and much stranger than that. They are not talking about an explosion tomorrow, or a catastrophe next year, or even something a human lifetime could possibly witness. They are talking about timescales so long that comparing them to a human life is a bit like comparing the age of a single snowflake to the age of a mountain. The numbers involved stretch so far into the future that our usual words for time, words like eventually, or someday, or a long while from now, start to lose their grip entirely, and scientists reach instead for exponents, for numbers written with strings of zeros trailing off the page. So before we go anywhere else tonight, before we talk about stars or galaxies, or the strange stretching of space itself, it might help to slow down and ask a simple question. What does it actually mean, in scientific terms, for a universe to end? What are we even talking about? The most basic answer is this. An ending, in this context, is not a single event. It is a direction. Physicists look at the universe the way you might look at a river from a bridge, noticing which way the water is flowing. And when they study the universe carefully, using light from distant galaxies, using the faint leftover glow of the very early cosmos, using the way galaxies cluster and drift apart, they find that everything seems to be moving in one particular direction. Not literally moving toward a single point, but changing, over and over, in the same kind of way. Stars form and burn and eventually go dark. Available energy gets used up and spreads out. Structure, which took billions of years to build, slowly comes undone. The universe, in other words, has a kind of grain to it, much like wood has a grain, and once you notice which way that grain runs, you start to understand where things are heading, even if you cannot say exactly when they will arrive. This idea has a name in physics, one that might be worth hearing gently, without any pressure to remember it. It is called entropy, and it describes something like the amount of disorder, or perhaps more helpfully, the number of ways energy can spread out and mix together in a system. Here is a small, human-sized way to picture it. Imagine a cup of hot tea sitting on a table in a cool room. If you leave it alone, it will not stay hot. Heat will drift out of the tea and into the room until the tea and the room are the same temperature. This happens every time, with every cup of tea, in every kitchen, and it never happens in reverse. A cooling cup of tea does not spontaneously heat itself back up by pulling warmth out of the room around it. That direction, from hot and organized to cool and spread out, seems to be one of the deepest habits of the physical world. Scientists sometimes call it the arrow of time, because unlike so much of physics, which works the same whether you run it forward or backward, this particular tendency only seems to run one way. The universe, it turns out, is behaving something like that cup of tea, just on a scale that makes a kitchen table look almost comically small. Stars are hot, dense, organized pockets of energy, doing work, producing light, holding together against their own gravity. But even stars, as brilliant and enormous as they are following the same basic rule as that cooling cup. They are burning through a finite supply of fuel. They are radiating their energy outward into the emptiness of space, where it spreads thinner and thinner, the way a drop of ink spreads through a glass of water until you can no longer tell where it started. Given enough time, and we are talking about numbers of years so large they are almost meaningless when spoken aloud, that spreading process tends toward a kind of stillness, not necessarily nothingness, not necessarily silence in every sense, but a kind of evenness, where there is no more hot and cold to create difference, no more concentrated energy to do the work that builds stars and warms planets, and, in at least one small corner of one ordinary galaxy, allows something like you to lie quietly in a bed and think about all of this. It is worth pausing here to say plainly that scientists do not know, with total certainty, exactly how this story ends. There are several serious possibilities that researchers have worked out using the tools of physics and mathematics, models built from real observations of real galaxies, but the universe is under no obligation to follow any single one of them precisely. Some possibilities involve the universe expanding forever, growing colder and emptier at an ever slower pace. Others involve stranger fates, tied to properties of space itself that are still being measured and debated. Over the course of this long, slow story tonight, we will walk through several of these possibilities together, unhurried, the way you might walk through a museum at closing time, when the halls are quiet and there is no need to rush from one room to the next. But the thread that connects all of them, the thing that makes this a story about an ending at all, is that direction we talked about a moment ago, the tendency toward spreading, toward stillness, toward less difference between here and there, hot and cold, full and empty. It is not a story about violence. It is not a story about the universe being punished or broken or destroyed by some outside force. It is, instead, a story about time doing what time seems to do best, which is simply continuing, patiently, in the same direction it has always continued, for longer than any of us can really picture, until the things that once stood out, stars, galaxies, light itself, gradually stop standing out at all. You do not need to hold any of this tightly tonight. There is no test at the end, no requirement that you remember the exact meaning of entropy or repeat back the arrow of time. All that matters right now is the simple, almost tender fact we started with. Somewhere, above the roof over your head, whether you can see the sky tonight or not, stars are burning exactly as they were an hour ago, exactly as they will be an hour from now, following that same slow, patient direction, while you rest here safely, changing far too slowly for either of you to notice. And it is with that image, stars burning quietly in the dark, unbothered by the hour, that we can start to look a little closer at what a star actually is, and why even something so bright, so steady, so seemingly eternal, is already, in its own way, beginning to end. Light, it turns out, is one of the most patient messengers in existence. It leaves a star, travels in a straight line unless something bends it, and arrives here carrying a kind of fingerprint of exactly what it passed through and where it came from. For most of human history, that fingerprint was read only by eye, a faint smudge of brightness against the dark, catalogued and named, and largely left at that. It took a particular kind of quiet, patient work, the kind that happens in cold observatory domes late at night, to realize that starlight was telling us something far stranger than anyone expected. The story usually begins with a man named Vesto Slipher, working at Lowell Observatory in Arizona in the early 1900s, a place chosen partly for its clear, dry air, and partly because Percival Lowell, who built it, was chasing his own ideas about canals on Mars. Slipher was not interested in Mars. He was interested in faint, fuzzy patches of light that astronomers at the time called spiral nebulae, small pinwheels of haze scattered across the night sky, whose true nature nobody yet understood. Were they clouds of gas inside our own galaxy, still being born, still taking shape? Or were they something else entirely? To find out, Slipher did something patient and unglamorous. He pointed his telescope at these smudges and let their light pass through a prism, spreading it out into a spectrum, the same way sunlight spreads into a rainbow when it passes through a raindrop. Buried in that rainbow of light are thin, dark lines, gaps where specific atoms, hydrogen, calcium, sodium, have absorbed specific colors on their way to us. Those lines sit in exactly the same places no matter where in the universe you find them, because hydrogen is hydrogen everywhere. They are like a fixed set of markings on a ruler, and what Slipher noticed, squinting at photographic plates that sometimes took all night to expose, was that in nebula after nebula, those markings were not quite where they should be. They were shifted, almost always toward the red end of the spectrum, as if the entire ruler had been quietly stretched. You have probably heard something similar happen with sound. A train passes through a crossing, its horn sounding higher as it approaches and lower as it pulls away, the pitch bending because the sound waves are being compressed ahead of the train and stretched out behind it. Light can do something comparable. When a source of light is moving away from you, the waves get stretched, and stretched light shifts toward red, the long, lazy end of the visible spectrum. Slipher was seeing, again and again, the signature of things rushing away from us, and rushing away fast, faster than almost anything else people had measured in the sky. What Slipher did not have, and what the puzzle still needed, was distance. Knowing that something is moving away is one thing. Knowing how far away it already is, and how that distance relates to its speed, is another. That piece came together over the following 2 decades through the work of several people, most famously Edwin Hubble, working at the Mount Wilson Observatory above Los Angeles, using at the time the largest telescope in the world, 100 inches across, hauled up the mountain in pieces, by mule and by truck. Hubble leaned heavily on a discovery made earlier by Henrietta Leavitt, an astronomer at the Harvard College Observatory who spent years studying a particular kind of star called a Cepheid variable, a star that brightens and dims on a steady, repeating rhythm. Leavitt noticed that the length of that rhythm was tied directly to how much light the star actually gives off. Find the rhythm, and you know the true brightness. Compare true brightness to how dim the star appears from here, and you can work out how far away it is. It is a bit like knowing the true wattage of a light bulb and then judging, from how faint it looks across a dark field, roughly how many hundreds of yards away it must be standing. With Leavitt's method in hand, and with careful measurements taken alongside his assistant Milton Humason, who had started at the observatory years earlier as a mule driver and worked his way up to running the telescope himself, Hubble began matching distances to the redshifts that Slipher and others had been recording, and a pattern emerged that was almost unsettling in its simplicity. The farther away a galaxy was, the faster it appeared to be receding, not roughly, not sometimes, consistently, proportionally, as though there were a rule underneath it. A galaxy twice as far away was moving away roughly twice as fast. Hubble published this relationship in 1929, though a Belgian priest and physicist named Georges Lemaitre had already worked out the theoretical reasoning behind it 2 years earlier, largely unnoticed at the time, using Einstein's equations of general relativity to argue that space itself might be expanding. That last detail matters more than it might seem to at first. It would be easy to picture this discovery as meaning that all the galaxies are flying outward from some central point, the way debris flies outward from an explosion, with us sitting somewhere near the middle watching everything rush past. But that is not quite the picture that held up. It is not that galaxies are racing through space away from us. It is that the space between galaxies is itself stretching, quietly, everywhere, all at once, and the galaxies are simply being carried along by it, mostly still, riding on a fabric that keeps getting larger. There are a couple of homely images that help here, and neither is perfect, but both are worth holding loosely as you drift. Picture a loaf of raisin bread rising in the oven. Before it rises, the raisins are scattered through the dough at various distances from one another. As the dough expands, every raisin moves farther from every other raisin, not because the raisins are swimming through the dough, but because the dough itself, the space between them, is swelling. A raisin sitting near the crust moves away from the center faster than a raisin sitting close to it, simply because there is more dough between it and everything else. No raisin is special. No raisin sits at the true middle. From the point of view of any single raisin, all the others appear to be moving away, and the farther ones appear to move away faster. That is very close to what we see when we look outward from Earth. It is not that we are at the center of the universe. It is that anyone, anywhere, looking outward, would see the same thing, every distant galaxy retreating, the far ones retreating fastest. A second image, a favorite among people who first teach this idea, is a balloon, with dots drawn on its surface, slowly being inflated. As the balloon grows, every dot moves away from every other dot, and again, no dot occupies a privileged center, because the actual center of the balloon exists in a direction the dots themselves, confined to the surface, cannot even point toward. It is an imperfect comparison, since a balloon has an inside and an outside, and the surface is only two-dimensional, while the universe, as far as we can tell, does not obviously have either of those things. But the core idea survives the imperfection. Expansion can be a property of space itself, everywhere at once, without there needing to be a center at all. This is where a distinction becomes worth sitting with quietly for a moment, the difference between the observable universe and the universe as a whole. Because light takes time to travel, and because space has been expanding for the whole time it has been traveling, there is a limit to how far we can possibly see, a kind of horizon, not because the universe stops existing beyond it, but because light from farther away has simply not had time to reach us yet, or in some cases never will, carried away from us by the expansion, faster than light can close the gap. Everything within that horizon, everything whose light has managed to arrive, is what astronomers call the observable universe. It is enormous by any human measure, tens of billions of light years across in every direction, and yet it is very likely only a small piece of something larger still, a universe that may extend far beyond what any instrument could ever detect, or that may, for all we currently know, have no edge at all. We are, in a real sense, looking out at a room lit only as far as the light has managed to travel, in a house whose full size we cannot see and may never be able to measure. Let's leave that unmeasured house for now and come down to something smaller, something we can actually watch happen in something like human time, or at least in stretches of time that astronomers have learned to piece together the way a geologist reads layers of rock. Let's talk about stars and about what it means for a star to run out of fuel, because in a real sense, this is where the ending of the universe actually begins. Not with a bang, not yet, but with something much quieter, a slow, patient exhaustion, repeated trillions of times over, star by star, across every galaxy there is. A star, at its simplest, is a fight. It is a battle between two forces that never stop pushing against each other for as long as the star lives. On one side is gravity, which is always trying to pull every particle of the star inward, toward the center, trying to crush the whole thing down into as small a space as possible. On the other side is pressure, generated by the heat of nuclear fusion happening in the star's core, pushing outward, trying to blow the star apart. For most of a star's life, these two forces are so evenly matched that the star simply sits there, glowing, seemingly unchanging, for what looks from the outside like a kind of eternal calm. But it is not eternal. It is a balance being maintained by the consumption of fuel, and fuel, no matter how much of it there is always a finite thing. Deep in the core, under pressures and temperatures that are difficult to even describe in ordinary language, hydrogen nuclei are being forced together to form helium, and in that fusion, a small amount of mass is converted directly into energy, which is the same energy that eventually makes its way to the surface and radiates outward as light, some of which, billions of years later, might land on someone's face on a summer evening. This stage, where a star is quietly fusing hydrogen into helium in its core, is called the main sequence, and it is by far the longest and most stable chapter in a star's biography. Our own sun is in this stage right now, and has been for about 4.5 billion years, and will continue in it for roughly another 5 billion, which is an amount of time so large that it is worth just letting it sit there for a moment, unexplained, uncompared to anything, because some numbers are more honestly felt than understood. But how long a star stays in this stable middle chapter depends enormously on how much mass it started with, and this is one of the more counterintuitive facts in all of astronomy, one worth turning over slowly. You might expect that a bigger star, with more hydrogen to burn, would last longer, the way a bigger tank of gasoline lets a car drive farther. But stars do not work that way, because a more massive star does not just have more fuel, it also burns that fuel far more aggressively, its core under so much more gravitational pressure that fusion runs at a much faster, hungrier pace. The result is that massive stars, the true giants, the kind tens of times heavier than our sun, burn through their hydrogen in a mere few million years, a cosmic instant, before their internal balance breaks and they move on to the more dramatic, more violent parts of their lives, parts we'll return to later in this telling. Stars like our sun, more modest in mass, take billions of years to do the same, and at the far, quiet end of the spectrum, there are stars so small, so miserly with their fuel, that they will outlast almost everything else in the universe. These smallest true stars are called red dwarfs, and they deserve a slow, careful look, because in the very long story of how the universe ends, they turn out to matter more than their modest size would suggest. A red dwarf might have only a tenth of the sun's mass, sometimes even less, and it glows a dim, deep red, dimmer than a match flame appears at a distance, though of course a red dwarf produces vastly more actual light than a match. It simply started from a much smaller reserve of fuel and spends it with extraordinary thrift. And here is the strange, almost beautiful part. Because a red dwarf is small, its interior is far more thoroughly mixed than a star like our Sun. Convection currents move material from the outer layers all the way down into the core and back again, in slow, churning cycles, so that virtually the entire star, not just a small central region, gets to participate in fusion over time. It is a bit like a campfire where, instead of only the wood right at the center burning while the outer logs simply sit there unburned, every log slowly rotates through the hottest part of the flame and eventually gets its turn. The result is that red dwarfs burn their hydrogen far more completely and far more slowly than larger stars do, and current models that of course rely on extrapolating physics we can only observe over much shorter timescales, suggest that the smallest red dwarfs could keep shining for trillions of years. Trillions, not billions. A single red dwarf could, in principle, still be quietly glowing long after every star like our Sun has gone dark, long after galaxies have drifted so far apart from each other that none of them can see the others any longer. This matters for a simple, almost accounting-like reason. Red dwarfs are also, by a wide margin, the most common type of star in the universe. Something like 3 out of every 4 stars in our galaxy are red dwarfs, small and dim and easy to overlook, utterly outnumbering the more famous, more sun-like stars that tend to get the attention. So when we ask when the last star will finally go dark, when the last true starlight anywhere will finally fade, the honest answer is not really about stars like the Sun at all. It is about these quiet, patient, deeply unglamorous little stars, doing their slow work of stirring and burning for spans of time that make even the age of the universe so far look brief by comparison. The universe as we know it now is only about 13.8 billion years old. The longest-lived red dwarfs may still be burning when the universe is 100 times that age, or 1,000 times. Numbers that stop feeling like numbers at all and start feeling more like abstractions, placeholders for a kind of time human minds were simply never built to hold. But even a red dwarf, however thrifty, is still spending something that cannot be replenished. There is no cosmic gas station. Once a star's hydrogen is truly exhausted, once there is no more fuel left to fuse in a way that can hold up against the relentless inward pull of gravity, the outward pressure that had been keeping the star in balance for its entire life finally, quietly, gives way. What happens next depends again on the star's mass, and it is worth sitting with the different possible endings slowly, one at a time, because each one is its own kind of quiet ceremony. Some stars swell first, puffing outward into something enormous and reddish before they finally cast off their outer layers, revealing a smaller, denser core underneath, a leftover ember about the size of the Earth, but almost impossibly heavy, a white dwarf, no longer capable of fusion, simply cooling, slowly, for an unimaginably long time, radiating away the heat it has left like a coal pulled from a fire and left in the yard overnight, except that this particular coal will still be glowing faintly, if you could somehow watch it, for far longer than the current age of the universe. Other stars, the heavier ones, end their lives far more violently, but that violence and what it leaves behind is a story for a little further ahead in this telling. For now, it is enough to hold this one image gently in mind as the fuel gauge keeps ticking downward, star by star, across the whole vast sky, Somewhere out there tonight, a red dwarf too dim for any unaided human eye to ever notice is patiently, unhurriedly, spending the first few billion years of a fuel supply that will not run dry until long after everything else we can currently see has already gone quiet. Let's stay with that image a little longer, because there is something worth noticing hiding inside it. Not every dim point of light out there is even a proper star at all. Scattered among the red dwarfs are objects astronomers call brown dwarfs, and they are strange in a way that is almost touching once you understand it. A brown dwarf is a failed star, though failed is perhaps too harsh a word for something that simply didn't happen to gather quite enough mass. It formed the same way stars do, out of a collapsing cloud of gas and dust pulled together by its own gravity, but it never gathered enough material for its core to reach the temperature and pressure needed to fuse ordinary hydrogen the way the sun does. Instead, it sits there in the dark, glowing a deep, dull red or even infrared, warmed only by the last heat of its own formation, and by a much slower, much less efficient kind of fusion, involving a heavier form of hydrogen called deuterium, which runs out quickly, in cosmic terms, within the first 100 million years or so. After that, a brown dwarf simply cools. It has nowhere to go and nothing left to burn. It will spend the rest of its existence gradually losing the heat it was born with, like a stone pulled out of a campfire that will still be faintly warm to the touch centuries from now, and warmer still, in its own dim way, for ages after that. There are brown dwarfs out there tonight, some of them closer to the sun than many stars you could name, quietly radiating away into the darkness, and they will keep doing this, essentially unchanged, for stretches of time that make even the red dwarf's trillion-year hydrogen supply look almost hasty by comparison. It's worth pausing on why this matters, because brown dwarfs are, in a sense, a preview of coming attractions. As the universe ages and keeps aging, fewer and fewer new stars are born at all. Star formation requires large, cold clouds of gas, mostly hydrogen, drifting through galaxies and slowly collapsing under their own gravity. And every time a new generation of stars is born, some of that gas gets locked away, either burned in stellar cores, or blown back out into space in less usable forms, or simply stranded inside the slowly cooling husks of dead stars. Galaxies do recycle some material when stars shed their outer layers or explode, but the recycling is never perfect. A little more gas is lost from the usable supply every time. So star formation isn't something that simply continues forever at the pace we see now. It has already been slowing down for billions of years, and it will keep slowing more and more as the raw material for making stars becomes rarer and more scattered. Astronomers sometimes describe the present moment, cosmologically speaking, as still relatively early, still within the first small percentage of the universe's star-forming lifetime, which is a strange thing to sit with on a clear night when the sky looks so timeless and so finished. It isn't finished. It's barely gotten started, and yet even so, the long decline has already begun. Picture it, playing out across a timescale so enormous that trillions of years become almost a unit of convenience rather than a shock. Somewhere around 100 trillion years from now, give or take, depending on exactly how efficiently the last reserves of gas get used up, the era of star formation will effectively end. Not suddenly, not with any kind of dramatic final flourish, but the way a fire dies down after the last log has been added and no one is left to bring more wood. The red dwarfs, those frugal, unhurried little furnaces, will be the last ordinary stars still burning, and even they, one by one, will finally exhaust the very last scraps of their hydrogen, swelling briefly, faintly, before settling down into their own version of a white dwarf, smaller and dimmer than the sun's future white dwarf, but shaped by the same basic physics. At that point, there will be no more new starlight being made anywhere. The universe will still contain enormous numbers of stellar remnants, the leftover embers of everything that came before, but the specific act of new hydrogen catching fire for the first time, the thing that has been happening constantly, somewhere, for as long as there have been stars at all, will simply stop. This is worth sitting with, because it changes what darkness even means. The white dwarfs left behind by stars like the sun, and eventually by the red dwarfs too, don't disappear. They cool. But they cool so slowly, over such staggering timescales, that even after tens of billions of years, some of them are still glowing, faintly, in the infrared, the very last heat leaking out of a star-sized object about the mass of the sun, compressed into something roughly the size of the Earth. It's worth imagining what that density actually feels like, if feeling is even the right word. A teaspoon of white dwarf material would weigh, here on Earth, something like several tons, the mass of a small car packed into a space you could stir your tea with. That's what's left when a star like the sun runs out of options. Not destroyed, exactly, but compressed down into something almost unrecognizably dense, held up not by fusion anymore but by a strange quantum mechanical effect, called electron degeneracy pressure, which is really just a fancy way of saying that certain particles refuse, as a rule of physics, to be squeezed any closer together than a certain point, no matter how hard gravity pushes. And so the star settles into that balance and simply cools from there, slowly, for a very, very long time. Current estimates suggest it could take something on the order of a quadrillion years or more for a white dwarf to cool all the way down to the background temperature of the universe around it, fading at last from a dim red ember into something dark and cold and essentially inert. An object sometimes called, appropriately enough, a black dwarf, though no one has ever actually seen one, because the universe simply isn't old enough yet. Not even close. Heavier stars leave behind something different, and even stranger. When a star considerably more massive than the sun finally runs out of fuel, and after it goes through the more dramatic ending we'll return to later, what can be left behind is not a white dwarf, but a neutron star, an object so extreme that it's almost easier to describe by comparison than by number. Imagine compressing something like 1.5 times the mass of the sun down into a sphere only about 12 miles across, roughly the size of a city, a place small enough to drive across in 20 minutes if there were roads on it, which of course there aren't, because the surface gravity is so immense that the whole idea of standing on it, or walking, or existing there in any recognizable form, falls apart instantly. A teaspoon of neutron star material would weigh, roughly, as much as a mountain. These objects, too, simply sit there afterward, spinning, in many cases, unbelievably fast, some of them completing a full rotation many hundreds of times every second, sweeping beams of radiation across space, like a lighthouse that happens to be smaller than most cities and denser than anything else known to exist. And like the white dwarfs, they cool, slowly, over spans of time that make even a quadrillion years feel like a passing afternoon. So this is the shape the universe is slowly settling into, star by star, galaxy by galaxy, fewer and fewer points of new light, more and more cooling embers left behind by the ones that already burned out, a sky that will, ever so gradually, over spans of time longer than anything easy to picture, stop making new fire and start simply holding on to the old fire's fading warmth. It will not happen quickly. It will not happen visibly, not on any time scale a person could notice, or a civilization, or even 1,000 civilizations stacked end to end. But somewhere in that unimaginably long stretch ahead, the last new star will ignite, and after that, there will only be the slow, patient dimming of everything that came before. And underneath all of this, quietly directing every part of it, is something that has nothing to do with stars specifically, and everything to do with the way the universe works at its most basic level. It's worth slowing down here, because this next idea is really the key that unlocks the whole story, the one physical principle that explains why stars burn out instead of burning forever, why neutron stars cool instead of staying hot, and why, ultimately, nearly every ending we're going to talk about in this long, slow account has the same underlying shape. The idea is entropy. It's a word that gets used loosely in everyday conversation, often to mean something like decay, or disorder, or a room that's gotten messy. And while that's not entirely wrong, it isn't quite what a physicist means either. The more precise way to think about entropy is as a kind of spreading. Energy, left to itself, does not like to stay concentrated. Given the chance, it moves from where there's a lot of it to where there's less of it, until it's distributed as evenly as it can possibly be. That's really the whole idea. Everything else is detail. Consider a cup of tea, freshly poured, sitting on a nightstand. The tea is hot, which means the water molecules inside it are jostling around with a lot of energy, and the air in the room is cooler, meaning its molecules are moving more sedately. Over the next hour, without anyone doing anything, the tea cools down and the air around it warms up, just slightly, by an amount too small to notice on your skin. Heat has flowed from the hot thing to the cold thing, and it will keep flowing until the two are the same temperature, at which point the flowing stops. Nobody has ever observed the opposite happen. Nobody has ever come back to a cup of lukewarm tea and found it spontaneously growing hotter while the room around it grows colder, drawing its heat back in from the air, gathering its warmth back into itself as if rewinding a film. It doesn't happen, not because it's forbidden by some cosmic rulebook exactly, but because it's so staggeringly improbable that in the entire history of the universe, it's essentially never going to occur even once. That last point is worth sitting with for a moment, because it's the part that a 19th century Austrian physicist named Ludwig Boltzmann understood more deeply than almost anyone before him. Boltzmann's insight, worked out through the 1870s, was that the reason heat flows the way it does isn't because of some special law forcing it to, but because of simple probability. There are countless more ways for energy to be spread out evenly among all the molecules in a room than there are ways for it to be concentrated in one small cup. When you have an enormous number of particles bouncing around, colliding, exchanging energy at random, the odds overwhelmingly favor them ending up in whatever arrangement has the most possible ways of happening, and that arrangement is always the spread-out one. It's a little like shuffling a brand new deck of cards. There's exactly one way for the deck to come out in perfect order, ace through king, suit by suit. But there are more shuffled arrangements than there are atoms in the observable universe. So if you shuffle a deck long enough, you will end up with a jumbled order, not because the universe is conspiring against neat arrangements, but simply because jumbled arrangements vastly, vastly outnumber orderly ones. Nobody has to enforce the outcome. The odds do all the work. Entropy, in this sense, is essentially a way of counting those odds, and the tendency for it to increase, for systems to drift toward their most probable, most spread-out configurations, is sometimes called the second law of thermodynamics. The name sounds formal, almost bureaucratic, but the law itself was actually recognized a bit earlier than Boltzmann's probability work. by a German physicist named Rudolf Clausius, who in 1865 was the one to actually coin the word entropy itself, borrowing partly from a Greek root meaning transformation. Clausius had been studying steam engines of all things, trying to understand why no engine could ever convert heat into work with perfect efficiency, why there was always some waste, some warmth that leaked away and could never be fully recovered and put back to use. What he found, almost as a byproduct of very practical, very industrial questions about pistons and boilers, was one of the deepest truths about how the universe operates at every scale, from the steam engine on his desk to the largest structures spanning the darkness between galaxies. And here's the part that matters most for a story about endings. Almost every physical process you can name creates a little bit of new entropy. Burning a candle, digesting a meal, a star fusing hydrogen into helium, even just talking, or thinking, or the small effort your own body is spending to keep you warm as you lie there listening. All of it is, in some small way, converting concentrated, usable energy into a more spread out, less usable form. And the important word there is usable, because entropy isn't really about energy disappearing. Energy, as far as physicists can tell, never disappears. It only changes form, moving from one place to another, from one kind to another. Entropy is about something quieter and, in a way, more final. It's about the loss of the differences, the gradients, the hot places and cold places, the concentrated pockets and empty spaces that make it possible to do anything with that energy at all. A furnace can heat a house because the furnace is hot and the house is cooler. Once everything is the same temperature, the energy is all still there, every last bit of it, but there's nothing left for it to do. It has nowhere left to flow. This is why an English astronomer named Arthur Eddington, writing in the late 1920s, gave entropy a phrase that has stuck ever since, calling it the arrow of time. Most of the basic laws of physics, the ones governing gravity or electromagnetism, or the motion of individual particles, don't actually care which direction time flows. Run the equations forward or backward, and they work equally well either way, which is a strange thing to realize, because it means that at the level of a single collision between two particles, there's nothing in the mathematics that says which direction is the past and which is the future. But entropy breaks that symmetry completely. A shattered teacup on the floor and the same teacup sitting whole on a shelf are not equally likely states to encounter, one after the other in that order. You will see whole cups become broken ones constantly. You will never see the shards leap up off the floor and reassemble themselves into a cup. That single felt difference, the sense that time moves in one direction and not the other, that the future is somehow separate from the past in a way that up isn't separate from down, seems to trace back to entropy, to this quiet statistical tendency for things to move from rare, ordered arrangements toward common, disordered ones, and never, in any observable case, the other way around. So when a star finishes burning and no longer generates new light, it's not really pulling energy out of the universe. It's just finishing the process of spreading that energy out, converting the concentrated fuel it once held into radiated warmth that drifts outward, gradually, into the vast coldness of space, where it will never be gathered back together into anything as tidy or as useful as a burning star again. And that same tendency, working across every particle and every photon and every scrap of matter, is the current that the whole universe is drifting along, whether it's a teaspoon of tea cooling on a nightstand or the light of the very last star fading into darkness. It's worth understanding this pull, this arrow, clearly, because everything's still ahead in this story. Every different way an ending has been imagined for the universe turns out to be, in one way or another, a story about where that arrow is, quietly, patiently pointing. Now, to understand where that arrow is pointing, we have to talk about something that took most of a century to notice, and that still, even now, resists easy explanation. We have to talk about the expansion of space itself, and about a strange discovery made in the final years of the 20th century that changed the whole shape of this story. For most of the history of modern cosmology, the expectation was fairly simple. The universe began, as far as anyone could tell, in an extraordinarily hot and dense state, and it has been expanding ever since, the way a cloud of smoke expands outward from a match the instant after it's struck. And because gravity pulls everything toward everything else, the assumption was that this expansion ought to be slowing down over time. All that matter, spread across all that space, tugging gently on itself, should have been acting like a hand on a thrown ball, gradually easing the outward rush, slowing it, maybe even eventually reversing it. The only real question, physicists thought throughout much of the 1900s, was how much the expansion was slowing, and whether there was enough matter in the universe to eventually pull everything back together into a final collapse, a mirror image of the beginning, sometimes called the Big Crunch. So in the 1990s, two separate teams of astronomers set out to measure exactly that. One team was led by Saul Perlmutter, working out of Lawrence Berkeley National Laboratory in California. The other was led by Brian Schmidt and Adam Rees, working with what was called the High Z Supernova Search Team. Both groups were doing something quite painstaking. They were hunting for a particular kind of exploding star called a Type Ia supernova, which has a useful property. These explosions tend to release almost exactly the same amount of energy every time, regardless of where or when they happen. That makes them what astronomers sometimes call standard candles. If you know how bright something actually is, and you measure how dim it appears from Earth, you can work out how far away it is, the same way you could estimate the distance to a candle across a dark field just by noticing how faint its flame looks from where you're standing. By comparing the actual distances of these very distant, very old supernovae with how fast the space around them appeared to be stretching, based on the reddening of their light, both teams expected to find evidence of that gradual slowing, that gentle cosmic breaking they'd been trained to expect. Instead, in 1998, both teams found the opposite. The most distant supernovae were dimmer than they should have been if the expansion were merely coasting along or slowing down. They were dimmer because they were farther away than a slowing universe would put them. The expansion of the universe was not decelerating, it was speeding up. This was, by most accounts, deeply unsettling news to receive. Imagine spending years dropping a ball to study how gravity pulls it downward, only to find, again and again, no matter how carefully you check your instruments, that the ball is accelerating upward instead. That was roughly the feeling. Scientists on both teams reportedly assumed, at first, that they'd made some error, some contamination in the data, some overlooked source of dust dimming the light in a way that only mimicked acceleration. They checked and rechecked. The result held. In 2011, Perlmutter, Schmidt, and Rees shared the Nobel Prize in Physics for the discovery, a discovery that had taken something everyone believed about the future of the cosmos and quietly turned it inside out. To explain what they'd found, physicists needed something that could push space apart with a force that grows stronger, relatively speaking, as space itself grows larger, something built into the fabric of empty space rather than residing in any particular object floating through it. They gave this thing a name that is, if you think about it for more than a moment, a bit of an admission of how little is actually understood about it. They called it dark energy. Not because it's known to be dark in the sense of absorbing or failing to emit light, but because it's dark in the older sense of the word, meaning hidden, meaning unseen, meaning outside the reach of direct observation. We don't detect dark energy the way we detect a photon landing on a telescope's sensor. We infer it entirely from its effects, from the way galaxies are drifting apart from one another faster than gravity alone can account for. And by current estimates, dark energy is not some minor correction to the universe's bookkeeping. It appears to make up somewhere around 70% of all the energy in the observable universe, dwarfing ordinary matter, dwarfing even the mysterious dark matter that holds galaxies together, that stuff you may have heard mentioned in other contexts, which is itself a separate puzzle from this one. Most of the universe, in other words, seems to be made of something that does the opposite of what gravity does. Where gravity draws things together, dark energy pushes them apart, and it appears to be winning. One useful way to picture the effect of dark energy is to imagine the surface of a balloon with small dots drawn on it, each dot representing a galaxy, and then imagine slowly inflating that balloon. The dots don't move across the surface of the balloon the way a marble might roll across a tabletop. The surface itself stretches, carrying the dots apart from one another as it does. That's closer to what's happening with the expansion of the universe than any image of galaxies flying outward through some fixed, pre-existing space, the way shrapnel flies outward from an explosion. There was no explosion in that sense, no blast center that galaxies are racing away from. Space itself is what's expanding, and the galaxies are, in a sense, just along for the ride, embedded in a fabric that keeps stretching beneath them. Now here is the detail that matters most for where this story is heading. If dark energy really behaves the way current observations suggest it does, remaining constant in density even as space itself grows larger, then the amount of it, and its outward push, doesn't dilute the way matter dilutes as space expands. A box of matter, stretched to twice its size, has the same amount of matter spread more thinly. A box of dark energy, stretched to twice its size, seems to just contain twice as much dark energy, still just as concentrated, still pushing just as hard, if not harder, which means the expansion isn't just continuing, it's compounding. Space is stretching, and the stretching is making more of whatever it is that stretches space in the first place, and that, in turn, accelerates the stretching further still. The consequence of this, played out across enormous timescales, is something astronomers describe using the idea of a cosmic horizon, and it might be one of the loneliest ideas in all of physics, though it unfolds far too slowly and far too gently for anyone alive today to notice it happening. As space between galaxies keeps stretching, and as that stretching keeps accelerating, more and more distant galaxies will eventually be carried away from us faster than light itself can cross the growing gap between here and there. This doesn't violate anything Einstein worked out about the speed of light, because it isn't the galaxies that are moving through space at some tremendous velocity, the way a rocket might. It's the space between us and them that's expanding, and there's no speed limit written into the laws of physics for how fast space itself can stretch. Once a galaxy crosses that threshold, its light can never reach us again. Not later, not eventually, not with a bigger telescope. It becomes, for us, permanently unreachable, sliding past a boundary similar in spirit, though not identical in cause, to the edge of a black hole, an edge past which no signal can ever climb back out. And so, galaxy by galaxy, cluster by cluster, The visible universe available to any observer anywhere is expected to shrink, not because things are being destroyed, but because they are drifting beyond the reach of light, beyond the reach of any possible signal or message or beam. It's less like objects disappearing and more like a room slowly filling with fog, where the far walls don't stop existing, they just stop being something you can ever see or touch or reach again. Long before that fog fully settles, though, something else will already be well underway, something that started, in a sense, billions of years before any of this stretching and drifting began. Because while galaxies are busy sliding out of reach of one another, the objects inside those galaxies are undergoing their own quiet transformation, one that has nothing to do with the expansion of space, and everything to do with gravity, doing what gravity has always done, which is pull. Stars, as you may already know, spend most of their lives in a kind of standoff. The core is trying to collapse under its own weight, and the fusion happening in that core is pushing back, radiating outward, with enough pressure to hold the whole structure up. It's a balance, and like most balances, it can't last forever, because eventually the fuel runs out. What happens next depends almost entirely on how massive the star was to begin with. Smaller stars, like the Sun, will swell up, shed their outer layers gently into space, and settle down into something called a white dwarf, a dense, slowly cooling ember about the size of Earth. But the truly massive stars, the ones many times heavier than the Sun, meet a far more dramatic end. Their cores collapse so completely, so violently, that not even the pressure of tightly packed subatomic particles can stop them. Gravity wins outright. And what's left behind is a black hole, a region where the pull is so strong that not even light, moving at the fastest speed the universe allows, can escape it once it crosses the boundary known as the event horizon. This has already been happening for a very long time. Our galaxy alone is thought to contain tens of millions of these objects, remnants of stars that lived fast and died young, scattered quietly through the disk of the Milky Way, most of them doing nothing more dramatic than drifting through the dark, invisible except for the way they bend light or tug at nearby stars. But over the unimaginable stretches of time we've been talking about, these scattered black holes won't simply stay scattered. They'll find each other. It's worth pausing on why that is, because it isn't obvious at first. Space is enormous, and even a galaxy's worth of black holes is spread across a truly vast volume, so you might expect them to just keep missing each other, drifting past, like ships, in a very large, very dark sea. But over trillions of years, small gravitational nudges add up. Every close pass between two massive objects exchanges a little momentum, slowing some down and speeding others up, and stars and black holes on the slower end of that exchange sink gradually toward the center of whatever galaxy or cluster they belong to, the way sediment settles to the bottom of a still pond. Not quickly, but inevitably, given enough time. Meanwhile, the ones that got sped up in these encounters can be flung outward entirely, sometimes ejected from their galaxy altogether, sent drifting off into the emptiness between galaxies with nothing left to orbit. The result, playing out over a timescale so long it makes the current age of the universe look like a single tick of a clock, is a slow sorting process. Black holes and dead stars migrate toward the gravitational centers of their galaxies, merging with each other along the way, growing larger with each collision, while a smaller fraction get kicked out entirely, left to wander the darkness alone. Astronomers estimate that this stellar dynamical sorting and merging plays out over a timescale on the order of 10 to the 20th years, give or take, which is a number so large it stops feeling like a length of time and starts feeling more like an abstract symbol. It doesn't help much to say it's 100 quintillion years. The number is really just a placeholder for saying longer than you can hold on to, longer than the word eventually was really built to carry. What emerges from this long sorting is something astronomers sometimes call the black hole era, a period in the far future where black holes are, in a real sense, the main characters left in the universe's story. Ordinary stars will have gone dark by then, their nuclear fires long since spent. Even the white dwarfs and neutron stars, the ember-like remnants of smaller stars, will have cooled and gone quiet, sitting in the darkness like coals that stopped glowing ages ago. Black holes, though, are different. They won't be doing much of anything either, at least not on any timescale a human mind is built to appreciate, but they'll persist. They'll be the last visible in principle structures anyone could point a hypothetical instrument at, if there were still anyone left to build one. And this is where a rather beautiful piece of physics enters the story, one that a physicist named Stephen Hawking worked out in the 1970s, sitting with the strange implications of combining general relativity, which describes gravity, with quantum mechanics, which describes the small, twitchy, probabilistic behavior of particles and fields. What Hawking found, somewhat to his own surprise at first, was that black holes are not perfectly, eternally black after all. Right at the edge of a black hole's event horizon, the vacuum of empty space does something it does everywhere, all the time, which is fizz with tiny pairs of particles, winking briefly into existence, and then annihilating each other almost instantly, borrowing energy for the briefest possible moment before paying it back. Ordinarily, this happens too fast and too locally to matter to anything. But near an event horizon, occasionally, one particle of such a pair can fall in while its partner escapes outward, carrying a small amount of energy away with it. From far away, that trickle of escaping energy looks exactly like faint radiation, glowing softly off the black hole. It's since become known, fittingly, as Hawking radiation. The catch, and this is the part that matters for a story about endings, is that this radiation carries energy away, and by Einstein's old and by now very familiar equation relating energy and mass, carrying away energy means carrying away mass. Ever so slowly, a black hole is losing weight. It is, in the gentlest, faintest, most imperceptible way imaginable, evaporating. For any black hole we could actually observe today, this process is so slow it might as well not be happening at all. A black hole with the mass of the Sun would take something on the order of 10 to the 67th years to evaporate completely, a number that dwarfs even the 10 to the 20th years it takes for black holes to sort themselves out and merge in the first place. And the very largest black holes, the supermassive ones sitting at the centers of galaxies, some of them billions of times heavier than the Sun, take vastly longer still, numbers so large that trying to write them out or picture them is really just an exercise in humility. Somewhere around 10 to the 100th years, give or take, depending on the exact mass involved, even the largest supermassive black holes the universe manages to build will have radiated away every last scrap of themselves, thinning gradually into nothing but a whisper of low-energy particles scattered across an already unimaginably empty universe. There's something almost tender about the mechanism, if you sit with it slowly enough. Nothing dramatic tears the black hole apart. There's no final explosion, no violent release, at least not for the enormous ones. It simply, quietly, loses a little more of itself with each passing eon. The way a puddle left in the sun doesn't vanish all at once, but recedes molecule by molecule, so slowly that if you watched it for an hour, you'd swear nothing at all was happening. Except here, The sun in question isn't sunlight at all, it's the vacuum of space itself, patiently, faintly glowing, one particle at a time, across a span of time so long that everything else we've discussed so far, all the stars going dark, all the galaxies drifting out of reach, will have already happened many times over before the first black hole even finishes its slow disappearance. And when the last black hole does finish, when even the most patient, most massive gravitational monument in the universe has thinned itself down to nothing, what's left behind isn't emptiness exactly. It's something stranger than emptiness. It's a kind of afterglow, a scattering of the faintest possible particles drifting apart from one another at speeds so gentle they hardly deserve the word motion at all. Photons, mostly, and a handful of other light, elementary particles, moving through a universe that has by then expanded to a size so vast that comparing it to anything from our own experience stops being useful. Even comparing it to a galaxy stops being useful. The particles are simply out there, alone, each one further from its nearest neighbor than our entire observable universe is wide today, drifting through a darkness that has no name yet because nothing has ever needed one. Think, for a moment, about what a photon actually is at that point in the story. In the early universe, photons were everywhere, packed together so densely and moving with such energy that the whole cosmos glowed like the inside of a furnace. Even now, tonight, as you lie there listening, photons from the early universe are still passing through the room around you, stretched by billions of years of cosmic expansion into the microwave background, a faint, static hum of radiation so uniform and so cold that it registers as barely more than a few degrees above absolute zero. That radiation is already ancient. It's already been traveling for the entire age of the universe as we know it, and yet, compared to what comes after the last black hole evaporates, that radiation is practically brand new, practically local, practically warm. The photons left behind in that far future are the opposite kind of light. They carry so little energy that calling them light at all starts to feel generous. Each one has been stretched by an expansion of space so extreme, so relentless, running for such an incomprehensible span of years that its wavelength has grown longer than galaxies used to be. If you could somehow gather up enough of them to notice, which you couldn't, because there's nowhere near enough energy left in any given volume of space to add up to anything perceptible, you still wouldn't see anything resembling light in any sense we understand. Our eyes evolved to catch a narrow, useful band of radiation bouncing off the world around us, tuned to the light of a particular yellow star. That entire concept, light as something you can see, something that reveals shape and color and distance, belongs to a much younger, much busier universe. In the era after the black holes are gone, light still exists, technically, in the sense that photons are still particles obeying the same laws they always have, but it no longer illuminates anything because there's nothing left close enough, or bright enough, or fast enough relative to anything else for illumination to mean anything at all. So what is actually out there, drifting through that vast, stretched darkness? Mostly, it's the most fundamental particles physics knows how to describe, photons, as we've said. Neutrinos, those famously shy particles that already pass through the Earth by the trillions every second, without most of them interacting with a single atom, will still be drifting along, now spread so thin and so far apart that the idea of them interacting with anything at all becomes almost meaningless. Electrons and positrons, the lightest charged particles that survive this deep into the story, will be out there too, or at least the descendants of whatever pairs still exist after everything heavier has long since decayed away. There may be a scattering of other exotic particles as well, depending on details of physics we haven't fully pinned down yet. Ideas like whether protons themselves are perfectly stable, or whether, given enough time, quite possibly an amount of time so long it makes even black hole evaporation look brief by comparison, they too eventually fall apart into lighter pieces. That particular question, whether protons decay, is one of the genuine open mysteries in physics. Experiments have been quietly watching enormous tanks of ultra-pure water for decades, waiting to catch a single proton in the act of disintegrating, and so far, not one has ever been caught doing it. Whatever the truth turns out to be, the far future depends on the answer, but either way, whether protons endure forever or eventually decay into lighter particles themselves, the destination looks much the same: a universe of light, isolated fragments, none of them able to reach or affect any of the others in any meaningful span of time. And then there is the vacuum itself, which turns out not to be as empty as the word suggests. Even in a region of space with no particles in it at all, no atoms, no radiation, nothing you could point to and call a thing, the vacuum still isn't perfectly still. Quantum mechanics, the strange and thoroughly tested framework that governs the behavior of the very small, tells us that empty space is always simmering, ever so slightly, with what physicists call quantum fluctuations. Pairs of particles can appear briefly out of nothing, borrowing energy for the briefest possible instant before vanishing again, a kind of restless, low-level static built into the fabric of reality itself. It sounds almost like magic when you first hear it described that way, but it's been measured, indirectly, through very careful experiments here on Earth. Things like the tiny, real forces that appear between two closely spaced metal plates in a vacuum, forces that arise precisely because of this quantum jitter. Space, it turns out, has never been capable of true, absolute stillness. Even nothing has a texture. In that final era, after the stars have gone out, after the black holes have finished dissolving, this quantum fluctuation may be the only real activity left in the universe. Not activity in the sense of anything happening to anyone, or anything meaningful occurring, but activity in the barest technical sense. A background hum of particles, winking briefly into being and out again across a darkness so complete and so cold that our language doesn't really have comfortable words for it. It isn't the plain nothing of a switched-off television screen. It's a nothing with structure, a nothing that is still, in its own faint way, quietly doing something, the way a completely dark and silent room still holds air pressure, pushing gently against your eardrums, even when there's no sound to hear. It's worth pausing on how strange this actually is, because it's easy to let the phrase near perfect darkness slide past without absorbing it. Near perfect, not perfect. There is a difference, and the difference matters, even if it's a difference that will never again be witnessed by anything capable of noticing it. A universe of true, perfect nothing would be uninteresting to physicists in a specific way, because true nothing offers no further questions. But a universe of near-perfect darkness, one still lightly seasoned with drifting photons, ancient neutrinos, the occasional decaying particle, and the constant quiet fizz of the quantum vacuum, is a universe that is still, in the most technical and unromantic sense, doing physics. The equations still apply. The particles still obey their rules. It's just that there's essentially nothing left for those rules to act upon, and essentially forever for them to keep not acting upon it. Now, everything I've described so far, the slow fading of starlight, the patient evaporation of black holes, that lingering quantum fizz in the dark, belongs to one particular story about how it all ends. Cosmologists call it heat death, or sometimes the Big Freeze, and for a long time it has been the ending that current evidence points toward most strongly. But it is not the only ending anyone has ever taken seriously, and it's worth sitting with the alternatives for a while. Not because they're more likely, but because understanding why they're less likely tells you something important about how scientists actually think about the future of everything. It's the difference between a guess and an inference, and that difference is where most of the real intellectual work happens. Consider, for instance, the opposite of everything spreading apart. What if, instead, the universe eventually stopped expanding and began to fall back in on itself? This idea has a name almost as old as modern cosmology itself: the Big Crunch. Picture the expansion of space as something like a ball thrown into the air. Throw it hard enough, and it keeps rising. But if gravity is strong enough relative to that initial throw, at some point the ball slows, pauses, and starts coming back down. Apply that same logic to the whole cosmos. If there were enough matter, enough gravitational pull packed into the universe, that pull could eventually overcome the outward rush of expansion. The galaxies that have spent billions of years rushing away from each other would slow, stop, and then begin, agonizingly slowly at first, to approach one another again. Distant galaxies would start to look less red-shifted and more blue-shifted, their light compressing instead of stretching, a signal that space itself was contracting rather than growing. Over unimaginable stretches of time, the universe would shrink back down, growing hotter and denser the way it once did in reverse, the night sky filling in with light instead of emptying out, stars and galaxies crowding closer, then merging, then dissolving into each other's fire, until everything that ever existed was compressed back into a single, searingly hot point, not unlike the one it apparently began from. Some versions of this idea even speculated that such a crunch might bounce, triggering a new expansion, a new universe, in an endless cycle of collapse and rebirth. It's a compelling image, almost comforting in its symmetry, the notion that endings and beginnings might simply be the same event viewed from different sides. For decades, this was a genuine contender, taken every bit as seriously by working physicists as heat death. Which one the universe would experience depended, in this framework, on a single crucial quantity: the overall density of matter and energy in the cosmos compared to a specific critical value. Above that value, gravity wins eventually, and you get a crunch. Below it, expansion wins forever, and you get something more like a freeze. It was, for a good while, treated almost like a coin that hadn't yet been observed to land, and different research groups spent careful, patient years trying to measure the universe's actual density precisely enough to know which future we were headed toward. Then, in the late 1990s, two separate teams of astronomers, working independently and measuring the brightness of a particular kind of exploding star called a Type 1Ia supernova, found something that surprised nearly everyone in the field. These particular supernovae are useful because they tend to explode with almost exactly the same intrinsic brightness, which makes them reliable distance markers, something like standard candles scattered across the universe that let you calculate how far away a galaxy is by how dim its light appears from here. The astronomers expected to find that the expansion of the universe was gradually slowing down, the natural consequence of gravity tugging on everything, gently applying the brakes the way you'd expect that thrown ball to slow as it rises. Instead, they found the opposite. The most distant supernovae were dimmer than they should have been if the expansion were merely coasting or slowing. Space wasn't just expanding, it was expanding faster and faster, accelerating, as if something were pressing down on the gas pedal rather than gently letting up. That discovery, which earned its principal investigators a share of the Nobel Prize in Physics in 2011, effectively closed the door on the Big Crunch as our universe's likely fate. Whatever this mysterious pressure is, one that appears to make up roughly 70% of everything, physicists gave it a placeholder name, dark energy, admitting honestly that the label describes an effect far more confidently than it describes a cause, and dark energy, as best as it can currently be measured, isn't diluting the way ordinary matter does as space expands. It seems to remain a fairly constant presence, like a low, steady hiss of static that doesn't fade no matter how far you get from its source, which means its outward push keeps winning against gravity's inward pull, and keeps winning by an increasing margin, forever pushing the galaxies apart just a little faster than the moment before. This accelerating expansion is exactly what leads toward that long, cold, freezing fate rather than a fiery collapse. It's part of why heat death currently sits at the center of scientific expectation rather than at the edge of it. But accepting that the crunch is unlikely doesn't mean the story is finished, because there's a stranger cousin to that accelerating expansion worth mentioning, one that depends on a detail we still don't fully understand: the exact nature of dark energy itself. If dark energy is perfectly constant, unchanging in strength across all of cosmic history, then heat death, in its patient, gradual form, is what waits at the end. But some theoretical models allow for the possibility that dark energy's strength might not be constant at all, that it could, instead, gradually increase over time. If that were true, the outward push wouldn't just keep pace with gravity, it would eventually overwhelm every other force in existence, including the forces that hold galaxies together, then the forces that hold solar systems together, then the electromagnetic bonds holding planets and mountains and bodies intact, and finally, in its last fraction of a second, the strong nuclear force that holds atomic nuclei themselves from flying apart. This runaway scenario has a suitably dramatic name: the Big Rip. In its account, rather than a slow fade into darkness and quiet, the universe would end in an ever-accelerating tearing, galaxies shredded first, then stars, then planets, then, in the final unimaginably brief instant, the very fabric of matter itself pulled apart atom from atom. It is a vivid idea, and it makes for a memorable image, but it currently sits well behind heat death in the ranking of likely outcomes, because the best present measurements of dark energy are consistent with it simply being constant, not accelerating in strength. Nothing in the current data demands a rip. It remains possible mostly because our measurements still carry real uncertainty, not because the evidence favors it. There is a third alternative that unsettles physicists rather differently, less through drama than through a kind of quiet, structural strangeness. It has to do with the possibility that the very vacuum of space, the one we've been describing as ceaselessly, faintly active even in emptiness, might not actually be sitting in its lowest, most stable possible energy state. If that's true, the universe as we know it could, in principle, be resting in something like a false calm, a shallow valley in an energy landscape that has a deeper valley somewhere beyond it. And such a state, physicists point out, wouldn't necessarily stay put forever. Let's turn now to something even quieter than dark energy, quieter than the slow stretching of space itself. Let's talk about the protons. You may remember, from earlier, that protons are supposed to be forever. Every chemistry textbook, every physics course, treats the proton as the bedrock of stability, the one piece of ordinary matter that simply does not decay. Electrons are stable. Protons are stable. Everything else in the atomic family, the neutrons floating free, the muons, the exotic short-lived particles that flash into existence in accelerators, They all eventually fall apart into something simpler. But protons, as far as anyone has ever directly observed, just sit there, unchanging, patient. The same proton in a hydrogen atom today was, as far as we know, exactly the same proton a billion years ago, and will be exactly the same proton a billion years from now. And yet, a great many physicists suspect this isn't quite the whole story. The suspicion comes from something called grand unified theories, a family of ideas that try to show how three of the four fundamental forces of nature, the strong force, the weak force, and electromagnetism, might actually be different faces of one single underlying force, a force that only looks separated into three because we're observing it at relatively low energies, the way ice and steam look like entirely different substances until you understand they're both just water. These theories are elegant in the way physicists use that word, meaning they tie together things that otherwise seem unrelated, and they make a great many successful predictions about how particles behave. But nearly all of them predict, almost as a side effect, that the proton should not actually be permanently stable. It should, very occasionally, decay into lighter particles. Now, when physicists say very occasionally, they mean something almost impossible to picture. The predicted lifetime of a proton, if it decays at all, is somewhere in the range of 10 to the 34th to 10 to the 36th years. Try to hold that number for a moment. The universe, at this point in our story, is already unfathomably old. But even the most extreme timescales we've discussed so far, the slow fading of the last stars, the black dwarfs cooling in darkness, are nothing compared to this. If you had a single proton and waited for it to decay, you would need to wait roughly a trillion times longer than the current age of the universe. And even then, you'd only have decent odds, not a guarantee. So how would anyone ever test something like that? You can't watch one proton for that long. No experiment, no laboratory, no human institution could last anywhere close to long enough. But here's the clever workaround physicists came up with. Instead of watching one proton for an impossibly long time, you watch an impossibly large number of protons for a comparatively short time. If you gather enough protons together, say thousands of tons of ultra-pure water, sealed away deep underground in an old mine to shield it from cosmic rays and background radiation, then even with each individual proton having only the faintest whisper of a chance of decaying in a given year, across that many trillions and trillions of protons, you'd expect to see a decay event every so often, if the theory is right. This is, in fact, a real experiment. Detectors like Super Kamiokande in Japan, a cavern lined with ultra-sensitive light sensors surrounding a tank holding 50,000 tons of pure water, have been watching, patiently, for decades, for the telltale flash of light that a proton decay would produce. And so far, nothing. No confirmed proton decay has ever been observed. This has ruled out some of the simpler grand unified theories, the ones that predicted decay would happen a bit sooner. But it hasn't ruled out the idea entirely. More sophisticated versions of the theory simply predict a longer lifetime, one still consistent with watching a giant tank of water for a few decades and seeing nothing at all. So the proton stability remains, formally, an open question. Perhaps it truly is eternal, undecaying forever. Or perhaps it does decay, just on a time scale so vast that human observation, even generations of patient underground detectors, could never catch it in the act, at least not yet. If protons do decay, though, the implications for the far future of the universe are enormous, because it would mean that ordinary matter itself has an expiration date. Every rock, every scattering dust grain, every black dwarf star, Everything built from protons and neutrons would slowly, atom by atom, over spans of time that make even heat death seem almost hasty, dissolve away. The black dwarfs we described earlier, the cold, dead embers of once brilliant stars, wouldn't simply sit in darkness forever. If proton decay is real, they would very gradually evaporate, their matter converting into radiation and lighter particles, until, after a duration so long it barely fits into any meaningful sense of time, nothing solid would remain anywhere in the universe at all. There's a fascinating intermediate stage some physicists have proposed along this road, something they call iron stars. Picture this. Long after the last conventional star has gone dark, long after white dwarfs have cooled into black dwarfs, quantum mechanics allows for an extraordinarily slow process where atomic nuclei, given enough time, enough patience, enough waiting, can occasionally fuse or rearrange themselves through quantum tunneling, gradually converting into iron. Iron sits at the most stable point on the whole periodic table, the point where nuclei have the least energy per particle, the calmest possible arrangement. Given a time scale of around 10 to the 1500th power years, an amount of time so large it makes proton decays 10 to the 34th look almost immediate by comparison, every black dwarf, every neutron star, every scrap of ordinary matter left in the universe would theoretically convert into solid iron. Cold, dark spheres of iron drifting alone through an empty universe, representing the most stable configuration matter can possibly achieve. And then, if proton decay is real, even those iron spheres wouldn't be the final word. Slowly, unimaginably slowly, they too would begin to evaporate as their protons decayed, until eventually, after a length of time that dwarfs every number we've mentioned so far combined, nothing but stray particles and radiation, spread thin across an endlessly expanding void, would remain. It's worth pausing here to say something honestly. Everything in the last few minutes, iron stars, proton decay timescales, the eventual evaporation of all ordinary matter, sits at the very edge of what physics can currently claim to know. These aren't predictions in the same way that, say, the sun's eventual expansion into a red giant is a prediction. That's built on physics we've tested directly, watched happen in other stars, confirmed again and again. Proton decay, by contrast, remains a theoretical possibility, motivated by elegant and promising ideas, but not yet confirmed by a single observed event. It may turn out to be true. It may turn out that protons really are eternal, and some other, subtler process ultimately governs the truly deep future. Scientists hold these possibilities the way you'd hold any careful hypothesis, taking them seriously, testing them where testing is possible, and remaining honestly uncertain everywhere it isn't. Which brings us to a question that sits underneath all of this, quietly, patiently, the way the best questions often do. How, exactly, does anyone reason responsibly about numbers like 10 to the 1500th power years, when the universe itself has only existed for about 14 billion? It's a fair question, and a good one to sit with for a while, in the dark, with nothing pressing on you but the shape of the thought itself, because the answer says as much about the nature of scientific knowledge as it does about the end of everything. Let's start with something almost embarrassingly simple. No human being, no instrument, no institution has ever watched a proton decay. No one has watched a black dwarf finish converting into iron, or a black hole finish evaporating, because these processes, if they happen at all, take longer than the current age of the universe by factors so large that writing them out feels almost like a joke, a string of zeros stretching past the edge of any page you could imagine printing them on. So immediately we have to ask, if nobody has seen it, and nobody ever will, In what sense do scientists actually know any of this? The honest answer is that they don't know it in the same way they know the boiling point of water, something you could check yourself tonight with a pot and a thermometer. They infer it, carefully, the way a detective infers what happened in a room from the traces left behind, the scuff on the floor, the angle of a chair, without ever having been there to watch it happen. Good detective work isn't guessing, it's reasoning from evidence you can hold, toward a conclusion you can't directly see, but which the evidence leaves very little room to doubt. Physics has always worked partly this way, even in cases far more familiar than the death of the universe. Think about the inside of the sun. Nobody has ever traveled there, obviously, and nobody ever will. Not with any technology we can currently imagine, not with the heaviest shielding or the cleverest engineering. And yet physicists will tell you, with real confidence, that the sun's core sits at around 15 million degrees, that it's fusing hydrogen into helium at a specific measurable rate, that it has enough fuel to keep doing this for another 5 billion years or so, give or take. How can they claim that confidently about a place they've never visited and never will? Because the physics connecting what happens inside stars to what we can measure from Earth is dense, overlapping, and mutually reinforcing, like a rope made of many separate threads, none of them strong alone, all of them strong together. We measure the sun's brightness, its mass, its size, the specific wavelengths of light it emits, each one a tiny thread of evidence. We know, from laboratory experiments here on Earth, exactly how hydrogen behaves under extreme pressure and temperature, because we have recreated slices of those conditions, briefly, in facilities built for exactly that purpose. We plug all of that into the equations of nuclear physics and gravity, equations tested and retested in countless other contexts, in particle colliders, in the orbits of planets, in the bending of starlight around eclipses, and the model that comes out matches everything we observe from the outside. When a model built from well-tested physics predicts things we can check, and those checks keep succeeding, again and again, in ways that would be strange coincidences if the model were wrong, confidence grows, even for the parts of the model we can never directly witness. The far future of the universe works on a similar principle, just stretched to a much more extreme degree, the way a single drop of ink diffusing through water can be modeled just as reliably as an ocean current, even though nobody has ever followed one molecule for the entire journey. Scientists don't claim to know that black dwarfs will convert into iron after 10 to the 1500th power years because anyone measured a black dwarf doing this. They claim it because the nuclear physics governing how atomic nuclei fuse and settle into their most stable configurations has been tested extensively in laboratories, in particle accelerators, in the interiors of stars we can actually observe today, close enough for their light to reach our instruments. That physics tells us iron 56 sits at the bottom of the curve of nuclear stability, the calmest, lowest energy arrangement nuclear particles can find, the resting point at the base of a very long, very gentle slope. We're not guessing that iron is stable. We know that quite precisely, the same way a chemist knows exactly which compounds are more or less likely to react, which mixtures will sit quietly on a shelf for a century, and which will not last the afternoon. What we're doing, in the case of the black dwarfs, is taking that solidly established piece of knowledge and asking how long it would take for extremely rare, extremely slow quantum tunneling processes, particles slipping through barriers that should be impossible to cross, to nudge every nucleus in a cold, dead star toward that final stable state. The physics of the nudging is well understood, even if the pace of it is almost impossible to picture. The time scale that comes out, absurdly long as it sounds, is simply what falls out of the math when you run those well-understood equations forward, patiently, term by term, the way a slow drip fills a barrel if you're willing to wait long enough to watch it happen. This is the crucial distinction worth carrying with you as you drift through the rest of this story. There's a difference between extrapolating well-tested physics forward in time and speculating about physics we haven't confirmed at all. The sun becoming a red giant sits comfortably in the first category. We've watched other stars like the sun do exactly this, in real time, through telescopes, thousands of them, at every stage of the process, scattered across the sky like a photo album of the sun's own future, each one a snapshot of what our star will eventually become. Iron star formation sits in a slightly more uncertain but still fairly solid version of the first category, resting on nuclear physics we trust deeply, tested in accelerators on Earth, even though the specific event it predicts, an entire dead star quietly rearranging itself atom by atom, is far beyond anything we can watch from start to finish. Proton decay sits somewhere else entirely. It isn't an extrapolation of confirmed physics forward in time. It's a prediction that follows from certain theories, grand unified theories that try to describe forces we currently see as separate: electromagnetism, the strong force, the weak force, as different faces of one underlying force. Theories that are elegant and mathematically appealing, but not yet verified by direct evidence. Scientists have actually built enormous, careful experiments to test this, because an idea this consequential deserves to be checked rather than simply trusted. Deep underground, shielded from cosmic rays by thousands of feet of rock, the kind of quiet that swallows almost every stray particle passing through the sky above, sit tanks holding tens of thousands of tons of ultra-pure water, watched over by sensitive detectors lining the walls like the inside of some vast, dark cathedral, waiting patiently for even a single flash of light that would signal a proton quietly ending its existence. Decades of watching, entire careers spent staring at instruments in the dark, and not one confirmed event. That silence has taught scientists something real, even in its absence, the way a long stretch without rain still tells a farmer something about the season. It's ruled out certain versions of proton decay theories, the ones that predicted protons should decay quickly enough that we'd have caught one by now, in a tank that size, over that many years. It hasn't ruled out slower versions, the ones that would only produce a decay event once every 10 to the 34th years or so per proton, which is exactly why the estimate lives where it does, at the edge of detectability, right where an experiment could plausibly still catch something if you waited long enough, or gathered enough protons in one place, or got a little lucky on a quiet night in a tank beneath a mountain. That's really the heart of how scientists distinguish between what's measured, what's inferred, and what's still unknown. 3 different rooms in the same house, each with a different kind of light. Measured means someone built an instrument, pointed it at the right thing, and recorded a signal, the light from a hydrogen atom in a lab, the flicker of a distant supernova caught mid-collapse, the faint hiss of the cosmic microwave background filling the sky, first picked up by accident in the 1960s by 2 engineers who thought their antenna simply had a stubborn noise problem, before realizing they were listening to the afterglow of the early universe itself. Inferred means taking those measurements, combined with equations we trust because they've passed test after test in other situations, and following them, logically, to conclusions we haven't directly observed, but which the evidence strongly supports. The way you can infer the shape of a whole staircase in the dark from the feel of just the first few steps under your feet. Unknown means exactly what it sounds like, an honest gap, a place where the theories diverge, where different frameworks give different answers, and where no experiment yet exists that could tell us which one, if any, is right. A door in the house that hasn't been opened yet and might stay closed for a very long time. The far future of the universe touches all three categories, sometimes within the same sentence, sometimes within the same breath. The expansion of space is measured directly through the light of distant galaxies stretching as they recede, shifting toward the red end of the spectrum in a way we can record and compare and trust. The eventual fading of starlight as galaxies use up their gas is inferred, confidently, from stellar physics we understand well. Watching, in slow motion across cosmic time, the same story unfold in galaxy after galaxy, we can already see growing quieter. The ultimate fate of protons, and everything that follows from it, the iron stars, the slow evaporation of matter itself, remains unknown, genuinely and honestly unknown, resting in that patient, careful space where good scientists are willing to say, "We don't know yet, and we may not know for a very long time, if ever," and where saying so is itself a kind of rigor, not a failure of one. And it's in that space of honest uncertainty, oddly enough, that some of the most interesting questions about the universe's ending are still quietly waiting to be asked. So let's come back. Let's come back from 10 to the 34th years, from proton decay and black hole evaporation, and the last cold photon wandering through a universe so empty it has forgotten what stars were. And let's come back to right now, to this moment, to a bed, to a room, to the sound of your own breathing. Because here's the thing about all of that vast future we've been walking through together. It's real. Or at least it's the most honest picture we currently have of what's real, built from measurements and inferences and careful, humble unknowns. But it's also almost unimaginably far away. Not far in the sense of distance, though it's that too, but far in the sense of time, in a way that human minds, shaped by lifespans of decades and civilizations that rise and fall in centuries, were never built to hold comfortably. We can write the numbers down, 10 to the 40th years, 10 to the 100th. Numbers so large they stop meaning anything specific and start meaning, simply, a very, very long time, longer than any story, longer than any memory, longer than the universe has even existed so far by a margin that makes the current age of everything look like the first fraction of a second after some other, earlier beginning. And yet, here you are, in the roughly right now of cosmic history, a sliver of time so early, so close to the beginning, that the stars are still burning bright, the sky is still full of galaxies close enough to see, and life, at least on this one small planet we know of, is not just possible, but flourishing, complicated, curious enough to ask questions about its own eventual ending. That's worth sitting with for a moment. Of all the almost incomprehensible stretch of time the universe will exist, we happen to be here now, near the beginning, in the warm part, in the part with light. The sun outside your window, or the one that rose this morning wherever you are, is a middle-aged star, about 4.5 billion years old, with roughly another 5 billion years of steady hydrogen burning ahead of it, before it swells and complicates things for the inner planets. 5 billion years. That number, on its own, felt enormous back when we first mentioned it. It's the kind of number that used to make people's heads spin, back before we'd walked together through numbers so much larger that 5 billion starts to feel almost intimate, almost nearby, almost like next week by comparison. That's one of the strange gifts of thinking about deep time. It recalibrates your sense of scale. A human lifetime, 80 or 90 years if you're fortunate, is impossibly short next to 5 billion years. And 5 billion years is impossibly short next to the trillions, and the trillions are nothing next to the Google, and the Google is a rounding error next to whatever number, if any, marks the true end of everything, if there even is one. But none of that distance makes any of it less real, or less worth understanding. Astronomers in the 19th century, people like William Herschel, cataloging nebulae through hand-ground telescope lenses, had no idea that some of those faint smudges of light were entire galaxies, whole islands of billions of stars sitting millions of light-years away. They were mapping something vastly larger than they knew, patiently, methodically, without the full picture, trusting that careful observation would eventually add up to understanding. In a way, that's what we've been doing across these 12 sections together, piecing together, patiently, methodically, a picture built from evidence, some of it solid and repeatedly confirmed, some of it still tentative, some of it honestly unknown, of where everything is headed, over a time scale so long it makes the age of the universe itself look young. And here's a comfort worth holding on to as you drift toward sleep. Nothing in any of that far future changes anything about tonight. The heat death of the universe, if that is indeed how things end, is not something that will ever touch you, or your children, or their children, or any being that will ever live and love and worry and rest on any world, anywhere, for as long as there are worlds like this one left to have people on them. It is so far removed from human concern that worrying about it would be a bit like worrying on a warm summer evening about whether the sun will eventually run out of hydrogen. True, yes. Important, in some cosmic sense, yes. But not something that needs to keep you awake, not something that has any bearing on how you sleep tonight, or how your week goes, or how your life unfolds. If anything, the scale of it can do something almost the opposite of frightening. It can be quietly steadying. Whatever is troubling you today, whatever loop of thought keeps circling back as you try to settle into sleep, exists inside a universe so large, so old, and so patient that it dwarfs almost everything we carry as urgent. That doesn't make your worries unimportant. It just gives them a little room to breathe, a little context, the way a small stone looks different in your palm than it does sitting on a beach that stretches for miles in either direction. The problem is the same size. The space around it just got much, much bigger. There's also something gently reassuring in how much of this story is still unfinished, still being worked out by real people, in real observatories and laboratories, right now while you rest. Someone, somewhere tonight, is looking at data from a telescope pointed at a supernova billions of light-years away, trying to measure whether dark energy's strength has changed even slightly over cosmic history. Someone else is deep underground, in a detector shielded by kilometers of rock, waiting, patiently, for a proton that may never decay, or may decay tomorrow, no one knows. These are not settled questions being recited from a textbook. They are open, living, human pursuits, carried forward by curiosity that has survived from Herschel's nebulae and Hubble's redshifts all the way to now, and that will keep going long after tonight, long after this year, quietly adding pieces to a picture too large for any one lifetime to complete. That's the real shape of this whole story in the end. Not a final answer, delivered and closed, but an ongoing conversation between careful observation and a universe that reveals itself slowly, reluctantly, one measurement at a time. We know the sun will grow old. We know galaxies will drift apart as space keeps stretching. We suspect, with real confidence built on real physics, that starlight will fade, that black holes will eventually evaporate, that even protons themselves may not last forever, and past that point, in the coldest, emptiest, longest stretch of time anyone has ever tried to imagine, we simply don't know, and that not knowing is not a failure. It's honest. It's where the frontier is. It's where the next generation of quiet, patient people, at telescopes and in laboratories and underground detectors, will keep looking. None of it needs solving tonight. None of it needs holding on to, as you let your thoughts loosen and slow. The stars are still burning. The sun will rise again in a handful of hours, on this ordinary, unremarkable day, in this astonishingly early, warm, living moment of the universe's very long life. Let the vastness of it settle over you, like something soft rather than something heavy. Let the numbers blur. Let the far future stay exactly where it belongs, unimaginably far away, while you stay exactly where you belong, here, now, breathing slowly, safe, warm, unbothered by anything that lies 10 to the 40th years from now. Rest well.